I want to start today with a simple linguistic puzzle. It's almost a test.
Okay, I'm ready.
I'm just going to give you one word, and you tell me what it means.
All right, hit me.
The word is light.
Light. Oh, wow. Okay, well, that's a problem right away. I mean, do you mean light as in not heavy?
Like a feather, yeah.
Or light as in illumination from the sun? Or, even light as in a pale color?
Exactly.
Okay.
Without context, you're just stuck. But if I say he turned on the light,
It's instantly clear.
yeah, the ambiguity just poof, vanishes. I'm talking about how much his groceries weigh.
Right. And for us, for a human brain, that happens in, what, milliseconds? We don't even realize we're doing it.
But for a computer, that exact same sentence is a huge headache. I mean, a massive one.
And that headache is exactly what we're digging into today. This is our deep dive into, well, what's it officially called? Word sense disambiguation.
It is a bit of a mouthful.
It is, but the core idea, the mission, is so important. It's basically the process of automatically figuring out which meaning, which sense of a word is the right one in a sentence.
And we're pulling today from some really great material, specifically the text word sense disambiguation, models, methods, and applications, and focusing on some work by Aneko Gear and Mark Stevenson.
And what's wild is that this is not a new problem. This isn't, a ChatGPT era issue.
Not at all. The source says this has been a recognized task for over 40 years. It was first identified in, 1955?
1955, that's ancient history in computer terms.
We're talking punch cards.
Exactly, room-sized computers. And it all came up because of the very first attempts at machine translation.
The moment they tried to teach a computer to translate between languages.
They just hit a brick wall. The classic example is the English word free.
Okay.
In English, we say a free prisoner, meaning liberty, and we also say a free gift, meaning it costs nothing.
Right. Same word, two totally different concepts.
But in French, they're different words. Free prisoner is libre.
Libre.
But free gift is gratuit.
So if the computer picks the wrong one,
the translation completely breaks down. You get a liberated gift or a zero-cost prisoner. It's nonsense.
So from the very beginning, computers had to learn to look at the neighboring words. Prisoner means think liberty. Gift means think money.
Precisely. But, language is usually way messier than that.
Well, let's get into that messiness, because the source makes this distinction that I found really useful: homonymy versus polysemy.
Yes, this is crucial for understanding the difficulty. Homonymy is actually the easier problem to solve.
That's when the meanings are totally unrelated.
Totally unrelated, no connection. The classic example is bank.
The edge of a river or the place with your money.
Exactly. And the words that surround them are completely different. For a riverbank, you get water, sand, fish. For a financial bank, you get money, loan, account.
The contexts don't really overlap, so a computer can spot the difference pretty easily.
Yeah, it's a clearer signal. But then you get polysemy, and that's where it gets really sticky.
Because the meanings are related.
They're related. They share some conceptual DNA. The source uses the word leak.
Okay, so a pipe can leak water.
Right, liquid escaping. But an official can also leak a document.
Information escaping.
And in both cases, the core idea is something that was supposed to be contained got out.
And that's hard for a machine because the surrounding words might be similar. You might see flow, source, pressure in both contexts.
Exactly. The vocabulary overlaps and the computer gets confused.
There was also regular polysemy, which sounded a bit more predictable.
That's a fun quirk of English. Think about animals that are also food.
Chicken, turkey, lamb.
Right. I fed the chicken versus I ate the chicken. It's a pattern. If a machine learns the rule for chicken, it can probably apply it to duck or turkey.
And just to make it even more complicated, there's metonymy.
Ah, yeah. Using a word to stand in for something else, like saying Wall Street is panicking.
Right. You don't mean the actual street is having an anxiety attack.
Yep. You mean the entire U.S. financial industry. A computer has to be explicitly taught that a place can stand in for a concept or a group of people.
So we have all these different flavors of confusion.
Yeah.
How did we first try to solve this? The first approach the source mentions feels very, academic.
You mean the knowledge-based approach? Yeah. It really gets going with the Lesk algorithm in 1986.
And I love this because the logic is so straightforward. Lesk's idea was basically, hey, we have dictionaries, let's use the definitions.
It's a definition matching game. The core idea is that the correct meaning of a word will have a definition that shares words with the definitions of the other words around it.
Okay, you have to walk us through the pine cone example. It makes it so clear.
It's the perfect example. So the computer sees the phrase pine cone,
2 words.
and it needs to figure out which pine and which cone. So first, it looks up pine in the dictionary.
And it finds what? A type of tree or?
A kind of evergreen tree or essence to waste away from sorrow.
Okay. Then it looks up cone.
And it finds a geometric shape or the fruit of certain evergreen trees.
And now it just plays matchmaker.
It compares the text, and it sees that the definition for the tree sense of pine has the word evergreen.
And the fruit sense of cone also has the word evergreen.
Bingo. Overlap. That's the signal. The sorrow definition and the geometry definition don't share any words, so they get ignored.
That seems so elegant. So why didn't we just stop there? Problem solved.
If only. The big flaw, as people like Banerjee and Peterson pointed out later, is that dictionary definitions are actually really, really short.
How short are we talking?
In WordNet, which is kind of the standard tool for this, the average definition is about 7 words long.
7 words. That's it. There's not much chance for an overlap there.
Precisely. The odds of 2 definitions using the exact same word, like evergreen, are surprisingly low. The writers might use synonyms like conifer in one and evergreen in the other.
And the computer would miss the connection.
Totally. So they came up with a fix called extended gloss overlap.
Which sounds like a fancy way of saying, look at more words.
That's all it is. Instead of just looking at the definition for pine, it also looks at the definitions of its relatives in the dictionary's hierarchy.
Oh, like its parent word, tree.
Exactly. Or its parts, like needle. Suddenly, you're not comparing 7 words to 7 words. You're comparing 100 words to 100 words.
It just increases your chances of finding a match.
Hugely. And later on, they even started using graph-based methods, like PageRank.
The same algorithm Google used for websites.
The very same. They treat language as a giant network and see which meanings are most connected to the words in your sentence. It gets very mathematical.
But eventually, the whole field pivoted. We went from looking things up in a dictionary to something more like how we learn.
We entered the era of supervised learning.
This is where you stop giving the computer a rule book and you just start giving it examples.
Yes, the big shift from being rule-based to being data-driven. You take a machine and you just feed it thousands of sentences where a person has already tagged the right answer. In this sentence, bank means river. In this one, bank means money.
And the computer's job is to learn the patterns.
To figure out why. It looks for clues, or what they call features, in the context.
I love the term they use for the simplest one, the bag of words.
It's a great name. You basically take the words around your target word, say 5 on each side, and you just throw them all into a metaphorical bag. You don't care about the order.
But order matters in language. Man bites dog is not dog bites man.
It is, but for just figuring out the topic, this method is surprisingly good. If the words money and account are in the bag, the topic is probably finance, no matter the order.
They do look at order too, though, with n-grams.
They do. An n-gram is just a specific sequence. Riverbank is a 2-word sequence, a bigram. The machine learns that that specific phrase points to the land meaning.
It's like a detective dusting for fingerprints. And this is where it gets really cool, because in the process, the researchers discovered these fundamental rules about how we use language.
The heuristics, yeah. The aha moments.
The first one is 1 sense per discourse.
This is just fascinating. Gale and his colleagues found that if an author uses, say, bank to mean river once in an article,
then they'll probably mean river every other time they use it.
There's a 98% chance they will. It's incredibly consistent.
Well, it makes sense. I wouldn't say I went fishing on the bank and then I went to the bank to cash a check. That's just confusing writing.
Exactly. We tend to be consistent. So for a computer, that's a massive shortcut. Figure it out once, apply it to the whole document.
And the second one was 1 sense per collocation.
That's from Urowski. It's the idea that words have neighbor habits. If bank is next to river, it's the land. If it's next to money, it's the building. That local context is incredibly powerful.
But all this supervised learning had one giant expensive problem.
The humans.
The humans. You need people to manually tag all those examples.
Hundreds of thousands of them. It's what the source calls the lexical acquisition bottleneck.
Which is a nice way of saying we're never going to have enough time or money to do this for every word.
It just doesn't scale. So you need a method that doesn't require a full-time teacher.
And that brings us to the third approach. Unsupervised, or minimally supervised learning.
And this leads us right back to Yurevsky, who came up with a brilliant idea in 1995 called bootstrapping.
I love that term. Pulling yourself up by your own bootstraps. How does an AI do that?
So imagine you want to teach it the difference between plant, as in a factory, and plant as in a living thing. But you don't have a big tag data set.
You just have a tiny little bit of information.
You start with just a couple of seed rules, tiny ones, for example. If the word manufacturing is nearby, it's the factory. If life is nearby, it's the organism. That's it.
Just those two words.
Just those two. The computer scans a giant pile of text and tags only the super obvious examples using those seeds.
Okay, so now it has a small, newly tagged data set that it made itself.
Right. And here's the magic. It then analyzes that new data. It looks for other patterns. It might notice, hey, in all these sentences about factories, the word equipment shows up a lot.
Ah, so it creates a new rule for itself. Equipment also means factory.
Exactly. It adds that rule to its list, then it rescans the text, finds more examples, learns more patterns from those examples, and it just repeats and repeats.
The snowball just gets bigger and bigger. It's teaching itself.
It's an incredibly powerful way to get around the bottleneck.
And then there's the purely unsupervised stuff, the word spaces. This feels like it's getting very abstract and mathematical.
It is. This is work by people like Schutze. In this case, the computer doesn't even know what the senses are called. It doesn't know one sense is money and one is river.
It just knows they're different.
It just knows they're different based on the math. It represents every context as a point in a high-dimensional space. And it just notices, okay, all these uses of bank are clustered together over here, and all these other uses are clustered way over there.
So it's like sorting books in a library by the color of their covers, without ever reading the titles.
That's a perfect analogy. It can tell the groups apart without ever knowing what the groups are about.
Okay, so we have all these methods, but we need to talk about the biggest context of all.
Right.
Not just the words in the sentence, but where the sentence came from. The domain.
Domain specificity, yeah, this is huge.
The classic example is bat.
Right. If I just give you the word bat, it could be a piece of sports equipment or a flying mammal. But if I tell you the document is from a baseball archive,
It's the wooden club, no question.
and if it's from a zoology journal,
It's the animal. The domain disambiguates it for you.
and this is absolutely critical in technical fields, especially medicine.
Oh, I can imagine. You really don't want to mix up meanings there.
Think of the word cold. Is it a temperature or is it the common cold virus?
Or a word like culture.
Culture in a sociology paper versus culture in a petri dish. Completely different. And that's why they built specific resources for this, right? Like the UMLS.
Yeah, the Unified Medical Language System. It's a massive specialized dictionary just for biomedical terms because the general ones just can't handle the jargon.
Okay, so we've built all of these amazing complex systems, but I have to ask the so what question.
Does any of this actually make my Google search better?
It's a surprisingly debated topic. You'd think the answer would be a definite yes, but the research is, well, it's nuanced.
Really? How so?
For search engines, some early studies found that even a perfect WSD system would only improve results by about 2%.
Only 2%. That's almost nothing. Why so little?
Because when you type a search query, you usually add other words that do the disambiguation for you. If you search for bank interest rates, you're not going to get articles about rivers.
The user does the work themselves just by typing a longer query.
Exactly. But later studies did show bigger improvements, maybe 7 to 14%, especially for really short queries.
Where there isn't much context.
Right, or for cross-language searches. If I search in English for bat but want Spanish results, the system has to know if I mean murciélago the animal or bait the club.
And what about machine translation, the original problem from 1955?
Also debated. Some systems didn't get much better, but others, especially for very different languages like English to Chinese, saw huge improvements. It seems the more different the languages, the more important it is to get the exact sense right.
So it really feels like we've come full circle. We went from literally counting word overlaps in a dictionary
To these incredibly complex self-learning systems that understand the statistical properties of language.
and now this tech is just everywhere, under the hood. That's why I can talk to my phone and ask for the new Jaguar, and it knows I mean the car, not the cat.
It lets us be lazy, it lets us be human, and it expects the machine to figure out the messy details.
We want the machine to understand what we meant, not just what we literally said.
Precisely. And the source hints at this at the very end. It talks about deep learning, creating these richer context representations.
Which got me thinking about something. The source says these new models map context mathematically as vectors in space.
Yeah, in hundreds or even thousands of dimensions, they see relationships we could never articulate.
So if a machine can mathematically map every subtle nuance of a context better than a human can, are we getting to a point where the AI understands what we meant better than we even realized we meant it?
That's a really provocative thought. I mean, we're not always conscious of the patterns in our own language. If the AI sees that 98% probability that we missed, maybe it does know us better than we know ourselves.
It sees the statistical truth behind our words.
Hmm.
A little bit scary, but also fascinating. That's all for this deep dive into the hidden world of meaning. Thanks for listening.